Welcome to English for Professional Mechanical Engineers. My name is Yiju. In today's lesson, we'll talk about another topic of microfabrication, deposition. These are the categories of microfabrication. It includes photolithography, deposition, and etching. We will focus on the second category, deposition, in today's lesson. But before deposition, let's recap the subject of photolithography. Last video, we introduced the first concept of microfabrication, photolithography. This technology transfers a micro pattern from a mask into a layer of photoresist. And what is a photoresist? It's a light-sensitive material. Finally, what are the machines for photolithography? It includes spin coater, wafer aligner, and exposure tool. I hope my rather rapid explanation was clear to you. Now, we'll move on to the second topic of microfabrication, deposition. This is the outline for this section. First of all, let me start by the definition of deposition. Next, I will talk about what materials can be deposited at the microscale. Then let's take a moment to look at a few machines, PVD or evaporation, sputtering, and CVD. Alright, let's move on to the first part, definition. Deposition, what does that mean? Deposit thin films of material anywhere between a few nanometers to 100 micrometers onto a substrate. There are two kinds of thin films deposition, as you may see in the table below, physical and chemical deposition. Physical techniques include evaporation or PVD, physical vapor deposition, and sputtering. Chemical techniques include chemical vapor deposition and atomic layer deposition. Next, let's look at what material can be deposited at the microscale. Okay, as you may see over here, there are a lot of materials. They include semiconductors like polysilicon, insulators like silicon nitride and silicon dioxide, and conductors like tungsten, titanium, and platinum. So, a lot of materials can be deposited on the surface of silicon wafer to serve as a key component in our smartphones, cameras, and game devices. After the definition of deposition and what materials can be deposited in microfabrication, we will discuss the methods and show the machines for doing deposition at the micro scale. There are three major methods. First, physical vapor deposition, PVD, or evaporation. Second, sputtering. And finally, CVD, or chemical vapor deposition. First of all, let's focus on PVD. What is PVD, or physical vapor deposition? At sufficiently low pressure and reasonable distance between source and wafer, the evaporant travels in straight lines to the wafer. There are some key points over here. 1. Low pressure. 2. Reasonable distance between source and wafer. The function of PVD can be demonstrated in this figure. First, a vacuum system at the bottom expels the exhaust to keep low pressure or vacuum in the chamber. Secondly, source material is at the bottom. On the other hand, wafer holder is at the top. The wafer are held upside down, face the source material. Next, when the source material is heated by resistance or E-beam, the material is evaporated and become atomic flux, which will deposit on the surface of the wafer. As long as distance between source and wafer is reasonable, a thin film layer of the source material will be deposited on the wafer surface uniformly. So, by relying on thermal energy supplied to the evaporate atoms, PVD is a method to deposit thin layers for microfabrication. Now, let's look at the second method of deposition for microfabrication, sputtering. First of all, sputter is not only for deposition, but also can serve as etchant. Then, sputtering can only deposit very thin layers. Usually, the film thickness is less than 10 nanometers. Next, it operates at low temperature. As a result, chemical reaction will not happen. It's a pure physical reaction. Finally, just like PVD, it also requires low pressure, but with plasma, a state of matter with extremely high energy. This is a photo of a sputtering machine because it requires low pressure and plasma. Lots of panels below can manipulate the physical parameters. The working chamber is the cylinder sitting at the top left of the panels. The structure of the cylinder is like the figure on the next page. Here you are. This is the working chamber of a sputtering machine or a sputter. First of all, it also requires a vacuum chamber with vacuum pumps. Then, power supply creates plasma in a high energy state. Next, target at the top while wafer at the bottom. Target material is expelled by the power supply to reach the plasma state. The high energy target material in the plasma state bombards the wafer at the bottom and is deposited as a thin film. Right, was that clear? Let's take a moment to recap the whole process of sputtering. 1. Vacuum. 2. Bombard the wafer with target material, and the target material is poured into the plasma state. So, what's next? Before looking at the final method for deposition, CVD, chemical vapor deposition, as you may be aware, the name of CVD is so similar to that of PVD, physical vapor deposition. Right. The major difference is that PVD works by evaporating a thin film on the substrate. On the other hand, CVD applied chemical reaction to form a new material layer on the surface of a substrate. So, the major difference between them is one with chemical reaction, CVD, while the other one is a pure energy response, PVD. Here is a device set up for CVD. Again, it requires low pressure or in a vacuum environment. Therefore, a pump on the right-hand side expels the air out of the chamber, with a pressure sensor on the left to ensure vacuum environment. Next, furnace at the top to maintain a high temperature for a proper chemical reaction. Finally, a gas inlet on the bottom left can intake some gas for the chemical reaction. Here is an example for growing a layer of silicon dioxide on the surface of silicon wafer. There are two ways to do it: dry and wet chemical reactions. Dry reaction needs oxygen, while wet reaction uses water. With the proper heating condition, a thin film of silicon dioxide will grow on the surface as shown in the figure. This photo demonstrates a CVD machine. Usually, it is complex and huge, with control panel on the left of the photo, and a deposition chamber like a channel on the right. Pipes and pumps can manage the intake of gas in a proper environment pressure. Alright, we have covered almost everything in this topic. It's about time to reflect what we have learned today. The topic introduced the definition of deposition, what materials can be deposited in the microfabrication, and finally, 3 methods and machines. Next, some questions to recap the main points of this section. Are you ready? Good, let's go. Question number 1, true or false? Microfabrication can only deposit film of a few nanometers onto substrate. True or false? Alright, the answer is false. It can deposit thin film of material anywhere between a few nanometers to 100 micrometers onto substrates. So, it's a broad range of the film thicknesses. Another true or false question for the subject of deposition materials. Only conductors can be deposited on the silicon wafer. True or false? The answer is also false. Let's look at the next slide. This page shows the materials which can be deposited for microfabrication. A lot of materials can be deposited on the surface of silicon wafer, including semiconductor like polysilicon, insulator like silicon nitride and silicon dioxide, and conductors like tungsten, titanium, and platinum. Next, we will look at deposition methods. What are the 3 methods to deposit thin films for microfabrication? Okay, the answer includes PVD, evaporation, sputtering, and CVD. Have you got the answer correctly? Good job. Okay, this is the end of the section, Introduction to Micro Deposition. So much for today. Thank you for watching. Hope you have learned something useful for this section. We are going to talk about the final part of microfabrication in the next video, etching. Have a good time and see you in the next one. Bye bye.